Out in the deep solar system, the sun is so distant that traditional solar panels capture almost no energy. If you want to keep a probe running out there for 2 decades, you typically need to pack heavy, incredibly expensive nuclear fuel. Hauling all that weight across the solar system severely limits what else your rocket can carry. That massive weight penalty is a severe problem when your target is Triton. Neptune's largest moon is a treacherous world, covered in slick nitrogen ice and violently erupting cryovolcanoes. Trying to softly land a heavy, wheeled rover on that unstable terrain requires complex landing engines and dense chemical propellant. It is a high-risk gamble where one wrong move easily ends the mission. Instead of fighting the environment, engineers propose a radical alternative. A sleek spacecraft acting as a magnetic glider lowers an incredibly thin 3,500-kilometer space elevator. By throwing out our standard chemical fuel tanks and heavy landing gear, we get a mission profile completely tailored to survive the outer solar system. The design works by parking a mothership in a synchronous orbit. It matches the moon's rotation, so it stays locked exactly 3,500 kilometers above Triton's equator. This shows why a massive cable doesn't instantly snap. On Earth, gravity pulls downward with immense force, but Triton's gravity is extremely weak, about 8% of home. Because of that minimal pull, a Kevlar tether easily supports its own length as it drops. At the bottom of that wire is a small atmospheric probe, but it never actually touches the ground. Instead, it acts like a hovering lure, dangling just meters above the ice. From this suspended position, the mothership can control the atmosphere. It drags the probe directly through 8-kilometer-high cryovolcano plumes to run chemical analyses in real time. The physical wire handles all the heavy lifting. It sends a continuous supply of high-voltage power down to the probe and acts as a fiber optic cable beaming data back up to the mothership without any signal loss. Yet, there is a much larger issue pulling on the entire spacecraft. Moving thousands of kilometers of wire through space generates massive drag against Neptune's magnetic field, and Triton's thin atmosphere pulls constantly on the hovering probe. If you look at this schematic of the spacecraft's orbit, you can see how the law of conservation of momentum plays out. These opposing forces continuously steal kinetic energy, generating a constant drag that guarantees the spacecraft will eventually drop into a fatal spiral and crash. The solution to this fatal orbital decay lies in the massive, wobbling magnetic field of Neptune itself. Orbiting through Neptune's magnetic field turns the conductive tether into a giant generator, charging onboard batteries. When altitude drops, the system reverses, pumping stored electricity back down the wire. This generates upward thrust, the Lorentz force, instantly lifting the spacecraft back to safety. The tether is doing the exact opposite of what a parachute does. It transforms the very drag that was pulling it down into an electrodynamic motor, pushing the ship forward without using a single drop of traditional propellant. The spacecraft operates in a continuous, perfectly balanced loop. It intentionally bleeds off its physical altitude to harvest electrical power, and then spends that stored electricity to boost its altitude back up. By managing this power cycle, engineers eliminate the heaviest and most limiting bottleneck in deep space exploration, the requirement to haul thousands of pounds of chemical rocket fuel. As long as Neptune's magnetic field continues to churn, this spacecraft has access to an infinite energy source to keep it flying. When the science mission at Triton is finally complete, the mothership simply reels the probe all the way back in. It seals the hangar doors and rides that magnetic thrust out into the dark toward its next target. By rethinking how we generate power and manage drag, we elevate disposable probes into self-sustaining exploration carriers. It pushes the lifespan of an outer solar system mission from a few short years to potentially several decades.